Good evening and welcome to Lowell Observatory's year-long celebration of the Lowell Discovery Telescope. It's year-long because this is the 10th anniversary of first light for the Lowell Discovery Telescope. It was in 2012 that our scientists and engineers first pointed the telescope in the sky, and it was capable of doing science. So it's really exciting because this is one of the most powerful telescopes in the world, and every month we have a different program in which we've been talking about how the telescope works, some of the unique characteristics, and of course the people that use it, both astronomers to do science, engineers to take care of it, and lots of other support staff and others. Tonight is going to be a lot of fun, I think, because just last month and up until a couple weeks ago, our team recoated the mirror, and we'll talk about what that means and why we have to recoat the mirror. But we've got a lot of great video taken by Nate Nice, who is on our broadcast behind the scenes, along with Maddie Mooney, making sure everything runs well. So we're going to share a lot of video tonight, and we're going to talk about the nature of recoating the mirror and why that's important for a telescope. So joining me tonight is Frank Cornelius, and Frank is the LDT engineering manager, and he's been working at Lowell Observatory for how many years?
Started in 2008, which I believe is about 14 years.
2008. Oh, and I see some of the time lapses were from Ryan also. So we've got a lot of really great video to show. So Frank, before we start the video, let's talk about what does it mean to recoat a mirror and why do we do that?
Well, the coating we have on there is a pure aluminum coating, and over time it wears out and we get things, mainly pollen, sticks to it. And the reflectivity starts to drop off over time. And so we want to freshen that up and get a better conditions for seeing.
And when you say that a coating, now we're talking about a piece of glass with a coating. How big is the glass, the mirror, we're talking about the primary mirror, and then how thick is that actual layer that you're recoating? So
the mirror is 4.2 meters. And
about 14 feet.
14 feet across, and it's about 4 inches thick. The coating we put on it is pure aluminum, and it's 1,000 angstroms thick.
So that's like,
which is a billionth of a meter, I think.
So we hold up this piece of paper, a typical piece of paper. It's 1,000 times thinner than this piece of paper.
Yes.
That's a pretty thin layer, and yet it's critical. Without that, you can't use a telescope. And so, how often do you recoat?
We've been able to go about 7 years between recoating. We do a water wash about 3 or 4 times a year, and that really cleans the surface off. But the surface does degrade over time. So after 7 years, we're due for a recoating. And
so we're talking about a 14-foot diameter piece of glass.
Yes.
It's not a simple process, is it?
No, nothing simple about any of this process.
So what we thought we'd start with is first to do a time lapse of the entire process, which is going to go through it really fast, and then we'll stop and show 5 different videos that go through the major steps. So let me just get our first video up here. This will just take a second to get this going here, and there we go. So this will be a full time lapse. The time lapse is a minute and 24 seconds, but of course, this is over days and days. So as we go along, this will be pretty fast, but maybe throw in a couple descriptions of what's happening, and then we'll go into more detail as we do the other videos.
So we're basically going to take the bottom half of the telescope off. We're disconnecting all the power supplies and all the air lines and the glycol lines and all that. And we take the mirror off when the telescope's pointing at the horizon. These are instruments that are coming off. This is the cable wrap that's coming off, the Cassegrain cable wrap. And this is the backside of what we call the mirror cell, and that's the big chunk of machinery that holds the mirror in position and positions it, so it's very safe when it's in the mirror cell. So we lower it down, taking it over to the coating chamber building. And we're prepping to take the mirror out of the cell. There's a lifting fixture that came down. There's the mirror by itself. And we strip the coating off, dry it off.
Well, that's a 14-foot piece of glass being held up.
And it's in the coating chamber, and that's a fresh coating. And then we're hoisting it back up into the observing deck to reinstall it onto the telescope.
It looks like a pretty fast process. What's the big deal with this? Well, let's stop sharing a second. We'll bring up the next video and we'll go through each step. Again, these will be time lapses, but we can go through that and then you can kind of pause as we're going with that also. And of course, throughout this program, we encourage our viewers to send in questions and we'll answer those as we can. And in fact, we have one question. Do you ever have problems with bat guano or bird droppings on the mirror that you need to wash it off?
Yes, we do. Recently, for many years, we didn't have any bats for some reason, and they have found the telescope now. And we've got a few spots of bat guano on it.
So what do you, that's just if you see it, you clean it immediately?
Usually, yeah. Or we do an aqueous wash to wash it all off. Aqueous wash is much better than trying to spot clean the mirror. It seems to work better.
And what does that involve?
Aqueous wash? It's just setting up scaffolding inside the telescope, and then we soak it down with water, and we have sea sponges that we plop onto the surface. We don't actually scrub the surface. We plop the.
Yeah, you don't want to scratch it.
We don't want to scratch the surface. Yeah. And that seems to get the bat guano off. And I've also put bat repellent. It's like a noise maker in the dome, and that seems to scare them off a little bit.
So do you have bats or birds that have nested in there?
No, no, they don't nest in there, but that I know of.
Yeah. They just want to see what's going on.
Yeah.
All right, let's go to our next video, and we have another question while we're getting that ready. It says you would have to be dust-proof, right? I think that's asking about the cleanliness of recoating and wearing bunny suits and such.
Oh, and for the coating process?
I think that's what.
We do everything we can to minimize the dust in the room. We seal off the doors, like the roll-up doors sealed off. And we put water on the floor so when you walk around, it doesn't stir up any dust. And then we limit entry in and out of the building when we're in the final steps of cleaning the mirror and getting it ready to go into the coating chamber.
And we'll see that a little bit in one of these later videos. This first one that we're going to show involves the preparation and disassembly of the telescope. So we'll start off, this is about a 4-minute video, and we'll start off with the telescope in regular condition, then you can kind of explain what you're doing. So
sure.
Here we go.
Yeah, so this is, again, we're disconnecting all of the support systems that go to the mirror. We've got compressed air, we've got glycol systems, we've got power that goes down there, all kinds of stuff. And we need to disconnect all that stuff to take the cell out.
And let's stop here for a second. Why do you have all that stuff in the telescope? The glycol and
it supports the instruments that are on the bottom of the telescope. They need glycol to cool the CCDs on the instruments.
And those are the CCDs are. What are those?
The cameras.
Yeah,
basically the cameras on the instrumentation. So those need to be cooled. We cool the bottom side of the mirror with glycol, so it tracks ambient temperature. And they obviously need power for that, and they need compressed air to run. They run slides and things like that with compressed air, and they spritz compressed air over the surface of the window of the cameras because those are at minus 120 degrees C. So if we don't spritz dry air over there, they'll get condensation on the mirror or on the window.
Certainly a lot more complex than our 24-inch refractor, which many people have looked through, and that's pretty basic.
Yeah,
compared to modern telescope.
And there's a lot of stuff going on in this
Let's
telescope.
start playing the video again.
So it looks like we have counterweights on the bottom side of the telescope to balance the telescope from over its axis. So it's balanced to within about 25 or 30 pounds. So this is, there's an aperture mask that covers the outside edge of the mirror and keeps stray light from coming in. So we're taking off the aperture mask at that point. They're panning. Looks like it's all still together. So we're still doing the support system. That's the instrument cube right there. There's about 5 different instruments on that at any given time. And we're still disconnecting.
How long did the preparation take just to disconnect all that stuff before you even took the cell out?
Just disconnecting stuff took about a day to disconnect and make sure everything was separate, because we still needed function on certain parts of the telescope to disassemble it. So we had to be somewhat careful about what we were disconnecting and what we left connected. And now looks like we're getting ready to start taking stuff apart on this.
And how many people are working on this?
We had about 8 to 10 people out there on any given day. Looks like we're down at horizon now. So we're going to start taking stuff off the back end of the telescope. And since we took all the weights off the bottom of the telescope was really out of balance. We probably took about 500 pounds of weight off the bottom of the telescope. So these guys are hanging on the telescope so it doesn't run away from us, because the top end is so much heavier now than it should be. So they're helping the motors so they don't overspeed and fault out.
Yeah. Yeah, you don't see that every day.
No, we're usually pretty well balanced most of the time. And that's a shot of the primary mirror before it gets the refresh coating.
Did you recoat the secondary also, or just the primary?
Just the primary. And that's the instrument cube that just came off. That holds all the suite of instruments. We have a couple spectrographs and the large monolithic imager.
So here's a slow.
Yeah, that's a slow motion of it.
Wow, that's a lot of equipment there.
Yeah.
So you don't take each instrument off first, or do you?
We did take most of the instruments off before we took the instrument cube off.
Okay.
It looks like most of them are off right now. So, and we're lowering it onto the cart so we can wheel it around. And now the next step is the Cassegrain cable wrap, and that's the round disc that's on the end of the. It's the round disc that's on the end of the telescope.
And what is the Cassegrain cable wrap?
It's basically a cable wrap that feeds all the power and the glycol and the compressed air and all that stuff into the instrument cube.
And I think this is important when we talk about that, where those cables go, because it helps you understand the nature of the mirror also with a hole in the middle. So maybe describe that and where the cables go to.
Oh, so the cables go to the instrument cube, which is positioned just below the center of the mirror, below the hole in the center of the mirror. And that's where the light comes down after it gets compressed from hitting the primary mirror to the secondary mirror. And then it comes down through the center of the mirror and it comes into the instrument cube. And so we can, depending on what instrument we use, they can do whatever, the scientists can do whatever they want with the light once it gets to that point.
Okay.
Yeah. And so this is a big piece. It's not super heavy, but it's really a flimsy piece to take apart. So that took us quite a while to get off. And then coming up through the center of the mirror is the stovepipe baffle. I guess we took that off. And so now this is the mirror cell on the back side of the telescope. Basically the whole back surface of that telescope is going to come off. And that is 27,000 pounds of steel and mirror. So it's a big piece, and we have to get everything disconnected and get the lifting fixture in position before we can start lifting it. And you can see the yellow beams above the telescope there are the bridge crane. And then we're getting the lifting fixtures in, and I believe there's over 120 20 bolts that hold that mirror cell onto the bottom of the telescope. So they're big.
What's the weight capacity of that crane?
It's a 15-ton crane, so it's a 30,000-pound lift that we can do with the crane.
And so that's how you lift it and then move it over to where you're going to lower it down.
Yeah, we lift the cell off. Once we get it unbolted, we lift the cell off, and then it drops down through the floor.
But probably not the term you usually use, drops down, right?
Right.
You slowly lower it.
Lower it down through the floor.
Right. And so now this process here, the preparation, before you got everything prepared, now you're removing all these pieces, getting the cell ready. How long did all this take?
The process up until this point was probably about 3 or 4 days to get all this taken apart. Each one of those big components, even though we have 10 people, it takes at least half a day to get it off and get it secure and to get it in a spot where you can store it for the next 10 days. So it takes quite a bit of effort to get everything positioned.
All right, let's turn off this video. And the next one will be lowering and moving the cell to the auxiliary building. And is this the most harrowing part of it, or is it all?
Well, actually, all of it is. I get more nervous when the mirror is actually out of the cell, because the cell is actually really good at protecting the mirror. It supports the mirror in many different ways, and there's earthquake restraints on it. There's all kinds of restraints on there that will keep the mirror in position. But once it's out of the cell, there's none of that stuff will protect it. And so you need to be much more careful about just walking around the mirror. If you have a ring on your finger, you could put a chip in the glass. There's all kinds of these things you have to consider once it's out.
Mm-hmm. Yeah. Let's see. We've got some questions coming in. Let's see. I think we can take a couple of these now. One, Phil from Phoenix. Any new instruments since the original setup of First Light?
We've got the same ones we've had since we started. We do have the Yale instrument is Express, which is a extreme precision spectrograph. That's from the Yale people.
And what's that used for?
Spectroscopy. Mm-hmm. Yeah.
And that's one of a major project. There's several major projects with it, but that one's exciting because they're looking for Earth-sized planets.
Yeah, it's the 100 Earths project is what they're working on. And then Gerard has his, it's called Dizzy right now, or is it Quizzy? One of the two, one of the versions. I'm not sure which one, but those are smaller instruments from our local astronomer.
And that's Dr. Gerard Van Bell, one of our scientists. Yeah. Here's a question from our good friend and educator, Claire. When the first LDT was first built, what was the thought process behind having a recoating facility with telescope versus outsourcing it? And maybe talk a little bit about the fact that this telescope is 40 miles outside of town, but our dark sky sites, where most of our research telescopes were closer, but we didn't do the recoating, then we used the Naval Observatory. So maybe talk about that a little bit. Maybe the history of our recoating and then why we decided to
keep it in-house.
Yeah.
I think one of the major things is the risk that you would take by putting the primary mirror into a crate, and the crate is going to be about 15 feet wide, and that's wider than one lane of traffic. So it would be a wide load wherever it went. There's the risk of being on the road with the mirror. And then there's the downtime of taking it apart and then sending it out to somebody for who knows how long it would take them to code it and then send it back.
Where's the closest place that could have been done? Is the Naval Observatory? Because historically, before the LDT, we sent our mirrors to the Naval Observatory, right, 4 miles west of the main Lowell campus.
The mirror we have is way too big for their coding chamber.
So where's the closest one if we had to outsource?
I'm not quite sure. It might be in Tucson, and I'm not even sure their facility would be large enough for us.
So the idea of taking the 14-foot piece of glass that's 4 inches thick, and sending it a few hundred miles. Yeah.
That would be a super big risk, I would think.
Yeah, sure.
Yeah. So the mirror will never leave the facility. It just has to make the trip from building to building.
Yeah, right.
Which I'll feel much safer about.
Well, Well, we have some more questions, but we'll show the next video and then get to some more questions. This is really fun to watch. So now we're going to watch the cell being lowered. So let me get back to sharing here. And here we go. This is about 3.5 minutes. Oops, I don't, just a second, I don't think I shared it. Just a second. Yes, hard to find good help. Okay, here we go.
So there we've got the cell all hooked up to the crane, and now we're lowering it back. We're bringing it back and lowering it down through the floor.
But not dropping it.
Not dropping it. You can see it swings around. It's what I said, it's about 27,000 pounds.
I'm gonna stop right here.
And there you can see the mirror.
In fact, let's go back just a little bit. And you can see how thin the mirror is. That's it right there. That's 4 inches, right?
Yeah, yeah. It's that black, the edge of it is black.
Mm-hmm.
And those are the lateral supports, all those aluminum boxes right next to it. So it's supporting the mirror.
And you wouldn't know it by looking at this. It looks like a perfectly fine piece of glass and mirror, but of course it's. How do you know when it needs to be recoated?
We take measurements off the surface of it, and we can measure reflectivity, and we also measure the amount of scattered light, which is created by when dust falls on the surface and then light hits it, it will scatter the light instead of reflecting it nice in nice smooth pattern. So we can measure the scatter, and once the scatter gets too high, we start losing a lot of light through the system. And there's the center holes where the light comes back through to the instrument cube. So it's lowering down. It's about 30 feet down to the ground level from where we had started lowering it. And this is called the mirror cart. And we bolt the mirror cell onto the mirror cart, and you can see it's stretched out right there on some railroad tracks. It's still in the vertical position. We're going to lower it to the horizontal position. And this is, I think that was me. There's some adjustment to get the mirror to hang straight up and down, and that's what we're working on right there. And this is the auxiliary building that is going to be our clean room for the next week or so. That's why there's a tarp hanging down in front of it so we can cover up the roll-up door. We're lowering the cell down, so it's going to be in the horizontal position onto its cart. This took us most of the day to get it off the telescope and down onto this cart. And now that we're onto the cart, we're disconnecting. We're putting foam pieces over the mirror surface so that when we transport it between buildings, nothing's going to fall on it. We're also worried about the focal point of the mirror, wherever it would focus 14 feet of sunlight onto that point. And if that point was on the building, it would burn a hole in the building. So we need to cover it up to keep it out of the sun and keep anything from dropping on the surface. And that's our pusher cart that pushes the cart across the way.
And how does that work?
It's just a little electric motor that pushes and pulls. There we go. We're going back across.
So he's kind of just guiding it.
Yeah. It doesn't want to track very straight, so he's having a difficult time. And there's where we're going, to the other building right over there. And now we're safe in the other building. And then once we're into this building, we're going to start disconnecting all the support structures that the cell has that's attached to the mirror. There's about 120 connections on the bottom of the mirror, individual connections on the bottom of the mirror, and there's 36 that are connected to the side of the mirror. Those silver boxes right there, each connected to the side of the mirror. And then there's also some earthquake restraints that we have to take off too.
Earthquake restraints. And what do those consist of?
Those are they just trap the mirror from the top of the surface. They hang over the top of the surface, so the mirror is fully trapped inside the cell.
Okay.
So even if the cell tipped forward, the mirror would still stay in the cell.
Okay.
So you could hang the mirror up, you could hang the cell upside down, and it would still stay in the cell.
All right, let's stop sharing this one and close that. So we've got disassembled, lowered the mirror, taken it over to the building where it's going to be redone. Let's stop and take a couple questions, then we'll start seeing the next process, cleaning. It is pretty fascinating. So here's a question from Bella. Is there a list of when you're working on the telescope from beginning to finish? Do you have a checkoff list?
Yeah, we do. We have a pretty, each time we do this process, I work on there's a manual that we work from, and it's a pretty detailed manual that we have. It's been evolving ever since the telescope was built.
How many pages?
It's probably about 50 pages.
Yeah.
Yeah, just for the disassembly. There's a bunch of other manuals that we have too.
Yeah. So we're talking about a lot of planning. Because there's so many different steps, and you're not going to just say next week we're going to do this. You have to plan. How far in advance do you plan it, and what do you base the timing of the recoding on? Like we did it. You did it in July.
Yeah, we try to do it during monsoon season because typically observing during that time is limited. It's so cloudy and rainy here, so we do it during monsoon season. But I have been planning for this project for about a year so far.
So in 3 or 4 years, you'll start planning for the next one.
Probably, yeah. Well, there's some supply chain issues that we had to get. I had to make sure I had aluminum to put onto the mirror, and I had to order all kinds of things, supplies, and make sure they were here during the week that we needed them, or the time that we needed them. So there was a big push to get that stuff ordered early.
Yeah. Okay.
Yeah.
Well, let's see what's next. And just a reminder for those watching, I'm with Kevin Schindler, the Historian and Public Information Officer here at Lowell Observatory. And I'm with Frank Cornelius, who is in charge of recoding the Lowell Discovery Telescope's mirror, a process that happens every 5 years or so. So let's go to the next step, which is actually cleaning the mirror. And we'll get this video. Oops. Going just a second here. All right. Drag that up there. Okay, so here we are inside of the coating, or inside of the building, the auxiliary building, and take it from there.
So it looks like we're still disconnecting all the connections we have that hold the mirror into the cell. The foam is still on it. So we should be taking that off here in just a second. I think we're taking some measurements on the position of the mirror in the cell also, so that when we put it back in, we can put it back in roughly the same position.
So you make fiducial markings, or?
Yeah, we have fiducials. Yeah, there's the lifting fixture just came down and we hooked it onto the mirror. Then we lifted it off, and now it's on the wash stand. So this is going back a little bit. Looks like we just lifted the mirror off of the cell.
What is this support? So there's something that went through the hole, and how does that work?
The lifting fixture for the primary mirror is actually bolted onto the cell, so it lives with the cell. And so when we go to lift the mirror off the cell, we unbolt it from the inner diameter of the cell, and it lifts up, and there's some Delrin pucks that come up and contact the mirror surface, and then that's how we lift it. Now he's moving the cell back over to the other building so we can lower it down on the wash stand. And you can see on the bottom of the mirror all the pucks. Those are the connection points that hold the axial supports. Each one of those has an individual stepper motor that drives the mirror into its proper position.
And that's the glory of computers, and why you can have a 14-foot piece of glass but only 4 inches thick, because those keep it in shape rather than sagging under its own weight.
Yeah, we would dictate the shape of the mirror based on where we put those positions. Now it looks like we've got it onto the wash stand, and we're taking the lifting fixture out. And there we can lift that fixture up and out, and the mirror lifting fixture is still sitting on the ground.
Yeah.
And so we're going to get ready to clean it. This is just a soap and water cleaning that we do first, just to get all the dirt and the pollen off.
Let's stop there for a second. So soap and water, you're spraying it on there.
Yeah, we use a optical grade liquid soap is what we put on.
And so how do you apply it and then take it off?
We just spritz it on with we have those soda kegs that are off to the left side there, and we spray a soapy solution onto it. And I don't think we didn't do any scrubbing on this one, did we? I think we do it again, and we do a little bit of scrubbing.
Yeah, okay.
But we're just basically rinsing off the big particles and the back guano. We're trying to dilute that a little bit and trying to get all the pollution that's on the surface of the mirror.
So you're going to clean the mirror before you actually strip it.
Yeah. We want to make sure we get all the particulate that's on there.
Well, what if you left that on there? What if it was still on there?
You have the potential of scratching the glass.
Mm-hmm.
Yeah, depending on what that is.
And what would happen if the glass was scratched?
It would show an imperfection on the coating, because the coating is so thin it would show any imperfections in the glass.
Okay, let's continue here.
Yeah, I think we washed it one day and then we came back the next morning, and it looks like we washed it again just to make sure it was nice and clean. And now we're putting our chemical suits on. This is, let's stop. Oh, so now we strip the mirror coating is actually off the glass surface at this point.
Just a little bit there.
Yeah, so this is we call this green river. It's like a mild hydrochloric acid is what we put on the surface, and it dissolves the aluminum. You can see we put tissue paper down on the surface, and then we add this stuff called green river to the surface, and it just sits on the surface and takes about 10 minutes, and it dissolves the aluminum. And then we come back and we rinse that off with water.
And then where does that go? You have like
down the
reservoir.
In the center, we put a skirt on the center hole there, and right above the center of the mirror is a drain that goes down to a holding tank that we have. And so all that gets put into a holding tank.
And then what ultimately happens with it?
The water that goes in there, we have that hauled off.
Yeah. Okay, let's see that again.
So there you can see that's a clear glass surface now. And this is, that was calcium carbonate that we put on. We scrubbed the surface with the calcium carbonate. We rinse it off.
When you say scrub the surface, what are you scrubbing it with the calcium carbonate? But what?
Oh, we use potassium hydroxide and distilled water with calcium carbonate. And we have these we use Swiffer mops, and we just slide it over the surface. We don't apply any pressure to it. We're getting ready to put the mirror into the chamber, so we lowered it in. We had trouble with the middle table there, and then it's in the chamber. Oh, so this is the slower version of that. So you can see we've got there's the support structure that's around the edge of the mirror. Those are all wrapped in foil, so those actually get coated with aluminum.
So you're standing in the middle of the telescope mirror.
I'm standing in the center of the mirror, yeah. And we're actually drying all the water off the bottom of the mirror, making sure everything's dry, because as soon as it gets into the coating chamber and we pull a vacuum, any water is going to start boiling and we can't get a good vacuum. And you can see all the supports. Those are the pucks that hold the axial supports. And now the mirror is in the chamber. Yeah. Oh, so we're getting ready to load it into the chamber. So we've got those support structures there. We call those wiffle trees. We lower it down. We try to get it centered on that bowl as the best that we can.
So if it's not attached, it's just sitting there.
Yeah, it just sits on those supports. Yeah. The mirror weighs about 7,000 pounds. So now we're blowing it off as it comes into the chamber, just to get any last possible dust that might have settled onto the mirror. And then we seal the chamber up.
So how long was that process from when you started cleaning it, then you came back the next day, and then stripping that off till it goes into the chamber?
That was about a day.
For all that was a day?
That was a day.
Okay.
Yeah, so we can strip the mirror, clean the mirror, get it dry, and get it into the chamber all in one day.
And even though that's a clean room, you want to minimize the amount of time the mirror is sitting in an open room, right?
Yeah. And you can see the floor's all wet there. We're trying to minimize any sort of dust from people walking around.
Yeah.
We spent a bunch of time cleaning that building before this whole process.
And so can you describe the chamber here? You can kind of see it. There are these tanks on each side, and how does that work?
Those are cryogenic pumps.
Mm-hmm.
Those are, they have carbon in there, and we cool those down to about 12 degrees Kelvin. And those pull a vacuum on the air that's in there in the chamber.
All right, let's stop this one. And I don't want to close that. All right, so we've got another question here. When you guys are redoing the mirror, when you're recoating it, what else is happening with the LDT? Because you're working on the mirror, but is there also work being done on the telescope itself while this is happening? Yeah, there was a bunch of cleanup work that was going on up on the observing level, cleaning the rest of the telescope, just cleaning the inside of the dome. We did a bunch of that work. And they were also working on the mirror cell that was back over in the main building, and they were calibrating the supports that support the mirror from the bottom. The axial supports is what we call those. Mm-hmm. Okay, we have a couple more questions, but I think we'll wait on these until the next. Oh, here's one we can answer now. From Bella: is the mirror flat or concave?
It's concave.
And by what? What's the angle?
I'm not sure.
Okay,
it varies depending on how far out you're from the middle.
Okay,
it's like a salad bowl basically.
Mm-hmm. Okay.
Yeah.
Well, let's now go to recoating the mirror, and we'll get into a couple of the other questions we have here. And this is an interesting process because you can't even see it happening, right?
No, everything once we start coating, everything gets coated in aluminum, including the port windows. So we can't even see into the coating chamber when the process is happening.
Yeah, so let's open this. We won't start playing it yet, but talk about that port window.
That's a port window so that you can see inside of the coating chamber. It's just got the little dial up there. It has a little shield that comes over and covers up the glass, or else the glass would get covered in aluminum. Everything in the coating chamber is covered in aluminum.
Okay, well, let's watch this process as much as we can.
You can see the outside of it. So it takes us about 6 hours to get the cryo pumps cooled down, and we have a mechanical pump that we're using to pull a vacuum on the system until the cryogenic pumps get cold.
Go ahead.
Oh, there's a lot of standing around and waiting for things to happen. Is what happens.
How long does it take for you to get it down to the proper pressure? The vacuum
takes about 6 or 7 hours to get down. It depends on the atmosphere. If there's a bunch of moisture in the air, like there is this time of year, it takes a little bit longer. That's liquid nitrogen fuming off of the cryogen pumps.
When it's 320 degrees Fahrenheit, that's cold.
Yeah, and that's looking in the coating chamber. You can see the glass on the bottom there with the hole in the center.
So that's your last view of it.
Yeah, that was the last time we got to see it. So this is the fresh coating that's coming out. This is one of the best moments of my job ever, is seeing a mirror coming out of the coating chamber. It's the cleanest it's ever going to be. It's super reflective, it's amazing.
And we'll talk about the process of what's happening in just a minute here. And let's just let this keep playing. So what happened? It went in. It was like a magic wand. I mean, it went in and it suddenly came out and had this spectacular mirror on it. What happened?
So the mirror goes in, we pull it back and pull all the air out of the chamber. We've got filaments in the top. We've got these, if I hold them up in front of me, you think you can see them. These filaments, they hold aluminum, and there's 120 of these up on the surface of the the top surface. And we basically heat these up. They're tungsten with aluminum wound in them, and we heat them up until they're red hot. And the aluminum liquefies first, and then it gets hotter, and it vaporizes. And we have this vapor cloud of aluminum throughout the coating chamber. And we have crystal rate monitors inside the chamber that measure how fast it's being deposited onto the surface and the thickness of the surface. And so when we're depositing aluminum down, we monitor those crystal rate monitors until we get to about 1,000 angstroms thick.
So how much aluminum are you talking about? This settling?
It's on the mirror surface. I did a rough calculations, and it's about the volume of 2 quarters spread throughout that whole surface, which is, I don't know how you'd ever spread that out. Yeah.
Yeah, how did they do it in the old days before you had, chambers like this? Let's stop this one.
But if you do a thicker coating, you lose the how smooth the glass surface is. So the thicker you go, the rougher the surface gets, because molecules just stack up on each other.
Mm-hmm.
So we try to keep it as thin as possible, but still reflective.
So here's a good question from Christopher. Has there ever been a problem during the process that you had to start over? And what would that problem be? You were talking about the thickness. It has to be the right thickness.
Yeah, the right thickness. That's one of the coatings we did was questionable on thickness. We had a variation across the surface from one side to the other, and we decided to accept that coating at that time. So that was okay. And then another time, we got water into the chamber, and as soon as we would get close to the vacuum we needed to start coating, the water would boil off, and we couldn't maintain that vacuum. Mm-hmm. And so we had to abort that coating process. And I think we opened up the chamber and dried stuff out, and then tried it again, and we were lucky that time we got it coated.
So explain again what happens if the coating is too thick or too thin.
You'd have to do it all over.
But what's the problem if it is? What would the results be?
Oh, if it's too thin, light will pass through the coating, and so you won't get all the light reflected back onto the instrumentation or to the instruments.
And then how about if it's too thick?
And if it's too thick, the surface gets rougher and doesn't reflect the light evenly. It won't reflect the blue wavelengths as well. Mm-hmm. So it's not a good reflective surface.
Yeah. Okay. So how much time has been taken up now? You got the thing recoded.
Yeah, so we're about halfway through the process, and we're at the end of 2 weeks right now.
So all you have to do is put it back together.
Yes.
Right?
It's reverse.
But that's half of the time.
At least half of the time, yeah.
And why is that?
It takes longer to take stuff apart.
Yeah.
And it does to put stuff together actually. Yeah.
Okay, let's go to that last step. And this is about a 10-minute video. And it's amazing each step. I mean, just taking it out and just recoding it and just clean it, each step is really critical.
Oh, yeah.
And then, of course, putting it back together. You've spent all this time, 2 weeks.
Yeah.
And now you want to get it back together. So let's take a look at that process. All right, here we go. So we're back.
So we got the mirror back into the cell. We brought it back over to the telescope building. So there was a day or two of just getting the mirror back into the cell before this part was shown. We had to reconnect all those connectors on the base, on the bottom side of the mirror. We had to reconnect all the laterals around the side of the mirror.
Will you reuse that foam, or is that you just get new foam next time?
No, we keep that foam all the time.
Mm-hmm.
Yeah, we store it. We put it in storage. You can see part of the aperture mask across the top of the mirror there is back on. So now we're lifting it up with the crane to get it hoisted up through the floor. We had something that stuck, so we had to go down a little bit.
So you don't want any birds flying through the dome right now.
No, not at all. I think we closed all the roll-up doors just to make sure there wasn't even a breeze going through when we were lifting this thing. And now we're adjusting it so it's going to hang straight up and down. The lifting point isn't in the center of gravity, so it tends to twist one way or the other.
Do you have support lines or something to keep it as vertical as possible?
Yeah, we do. And then we put a level on it to make sure it's hanging straight up and down before we start raising it up. Looks like we're taking lunch. Something's going on. Nobody's around.
So nobody's allowed to get sick during this time, right?
No, you can never take a sick day. Oh, there we're coming back. And then we raise it up, and we've got to figure out how to get it disconnected from the cart. There, we got the cart out of the way. Now it's up through the floor. This is a shot looking down on the crane hook. So there we hooked it onto the mirror cell with the lifting fixture. And the chain is connected right to the cell. And you can see we're going to start lifting as we go up. The image on the right is a reflection of the mirror. It's kind of hard to tell. You can see it going up, and it's almost getting vertical. And that's where we had to lower it down a little bit.
And you said that's 30 feet or so you're raising it? Yeah,
it's still on the bottom floor, still connected to the cart at this point. So we're getting ready to level it out. He's going to make the adjustment. See there, you can see it go vertical.
Yep.
So that's the vertical. So when you put it back on the telescope, if it's sitting vertical, we can line it up and just slide it right in. There, he's going back a little bit more to make it vertical. He's doing adjustment. That's Jared, machine shop, machinist. There, see, he adjusted it way back.
It really takes an army to do this.
Oh yeah, that's hard work. Adjustment. You're 20 feet up on a ladder, doing those adjustments. And we should be getting ready to go up here in a second. We took a break, evidently.
And this is the highlight footage. This month-long process. We had Nate and others out there capturing this the whole time.
Yeah, there we're going up through the floor. We're up on the observing deck. And then you can see on the top there is the bottom of the telescope. So we have to line it up with those. There's about 1/2 inch on either side of the mirror as you go into the telescope. And there's a big pin right there that we have to align.
How long does it take to get it exactly lined up so you can?
It probably took us about an hour once we got close to the telescope, because you're supposed to bring it in, and then the thing weighs 27,000 pounds, but you're supposed to load those pins with 500 pounds of weight on either side, and there's a pin on either side, and that locates the mirror into the cell. And now we've got the pin located into the cell, and we're starting to put bolts in to attach the mirror cell to the telescope. That's what Jared's doing right there. We're lowering the fixture back down because we don't need those anymore. So
it's back in place.
The mirror's back in. There was a ton of stuff to do still. We still had to put on the Cassegrain rotator and the instrument cube and all that other stuff. So it was another week of just assembly after that step, after that video.
Yeah.
So.
And here's a question from Ben, if you want to take that.
New aluminum coating is sufficient thickness quality before reassembly. So we take, inside the coating chamber, we have these little sample slides that we put in there, and we measure the thickness. We put a razor blade halfway across the mirror, the little sample slide, and we coat. And then we take the razor blade off, and it leaves a step in the coating thickness. And we go to the MPUI, and we borrow their Zygo interferometer, and we can measure that step. And we shoot for 1,000 angstroms. And we were close, very close this time.
So how many times have you recoated the mirror so far?
I believe this was the third time.
Or coated it, I guess. You coated it first.
The first time, yeah, and that lasted about 6 years, 5 or 6 years. We recoated it again, and that lasted the last 7 years, and now we just recoated it again.
So when we come back here to celebrate the 50th anniversary of First Light, you'll have coated it several more times.
Yes, probably. It probably won't be me though.
8 or 9, 10 times. So what have you learned along the way, those 3 coatings, you know, the original plans and then having done it 3 times now? Were there any things that you learned that, oh, we found a different way, a better way of doing it? Or was the original procedure pretty much what you followed? Did you have to tweak it much?
For running the coating chamber?
The whole thing.
Or the whole thing.
Process.
We tweak, like the disassembly process, we've tweaked that a ton. And every time we do it, we take notes and we try to improve it and make it better. We've made fixtures just to store stuff easily. And so the whole procedure is much better. And this time we even had paint pens. We walked around and marked certain locations of the telescope for when we want to put a fixture back on. So we're doing all that stuff.
And you said in between, there's cleaning that you do a few times a year.
We try to wash it with soap and water at least 2 times a year, maybe 3 times a year.
And then if you do have a bat or a bird.
Yeah, we'll wash it sooner.
Yeah.
Yeah, you don't want to leave that stuff on. If we get ash from a fire on there, we'll wash it as soon as we can.
And we've had a lot of fires this season.
Yeah.
How was LDT affected by those?
We did have some ash on the mirror a few times. And so we washed it pretty much within a day or 2 after that. I think this last year, because of all the fires, we washed the mirror 4 times this last year.
Yeah.
It doesn't hurt it to wash it. Doesn't wear it out.
How many people does it take to do that and how long?
It takes us about 4 or 5 hours to wash it. And we do that early in the morning and they're back on sky the same day. We have a crew of about 4 people to do it now. We've got it pretty efficient setup.
Okay, here's a question who from the username is HarryToe1, who just tipped us for this fine program. What's it cost to recode it?
Oh,
there's a lot of
there's a lot of manpower that goes into it. The material costs to run the coating chamber is probably $4,000 or $5,000, I'd say, off the top of my head, with consumables and aluminum. All the materials we need.
And then a month of time. Many people.
A month of labor. For that many
and
people.
is there an endowment or funding to cover the cost of maintenance? How does that get paid for? Do you know?
I'm not sure.
Okay, that's right. Yeah.
I'm not sure about that.
But it goes into the cost of operating a world-class telescope.
Yeah.
Here's another question from, I want to get to Cody's. You may or may not want to defer this, but Cody's question is, in your mind, what's the neatest discovery LDT has made so far?
Oh, I'm not sure about that. I don't know.
Well, next month we're going to have one of our astronomers here, and we can talk about that a little bit more.
You can probably answer that, I'm sure.
Okay, here's a question from David. The small amount of aluminum that you use, does it have to be a higher grade than what's used in soda cans, for example? And how much does that amount cost?
Oh, yeah, the aluminum we use is 99.999% pure aluminum. So it's very pure aluminum. The filaments themselves probably cost about $2,000 or $3,000 for the filaments.
For all 100.
For each time we run the chamber.
Yeah. And the filaments are one time, then they're done.
Yeah, we can only use them once. We've got boxes of used filaments sitting around. We don't know what to do with.
Yeah, they're good. There was one of our supporters who, I think she did a tour years ago, and she had several of the used ones. I don't know if you can see. I think that works better when you were holding it in front of you.
Oh, here, I got one right here. Yeah. These are the ones we're using.
And she made a Christmas ornament out of them.
Oh, yeah.
And I thought that was pretty clever.
Yeah.
But yeah, after they're used, that's it.
Yeah, the aluminum's spent out of them, so we can't really use them again.
So these filaments, what are they typically used for? Are they specially made for?
Custom made for us. Yeah, we have the number of the number of coils that we have across here
Mhm.
is a distinct amount, so we have the proper resistance across the coil. So these are custom made for us.
Where are they made? Do you know?
I forget the name of the company that makes them for us. They make a bunch of these though.
Yeah.
Yeah, for a bunch of different companies.
So this is a standard.
That's Midwest
Sort of a-
tungsten.
Okay. This is kind of a standard filament used for different.
Yeah. Yeah, they basically make the
applications.
wire, and then they custom twist it for us.
Yeah.
And the length, and they make the length correct for us too.
Mhm.
So.
And here's a question from Phil, getting back to washing the mirror. And his question is, can you wash the mirror in place? And maybe you were talking about washing it before, but maybe elaborate, what position the telescope is in, and that you don't have to remove it.
Yeah. So we put the mirror is facing straight up and down. And we have, and so we put like in the center hole, we have a rubber thing that we put on. And then we have scaffolding that we build around the mirror. And then we just spray it with soapy water, and we have sea sponge that we blop onto the surface. And all the water runs down the mirror onto the floor below us. And we've gotten the process dialed in so that we only use about 4 or 5 gallons of water.
Mhm.
So we have a shop vac down there that we soak up the water with.
And you have like a kiddie pool or something where you use to collect the majority of the water?
We string a big tarp across the base of the telescope, and we put a board in the middle, and all the water goes to the middle, and we just have a shop vac in the middle that we suck up the water.
Okay.
So it's a good
It
process.
works nicely.
It works great. Yeah, it's amazing how dirty the mirror can be, and then we aqueous wash it, and it looks like it's brand new every time.
Yeah, that's a nice feeling.
Yeah.
We were talking before, you said maybe the most harrowing time is when the mirror is out of the cell.
Oh yeah.
And have you ever, you have so many safety things in place.
Yeah.
Have you ever had any issue somebody dropped a screwdriver or something? You have so many safety precautions that almost is impossible to happen.
Yeah, we've had a couple of, we had a chip that we found in the mirror one time, and we're not even sure how it happened. But we have to take if there's a chip in there, it's a stress concentrator. So that I had to take a Dremel with a diamond ball mill, and grind out the chip so that it wouldn't form any cracks. And that was nerve-wracking, to say the least.
When you think about, the thinness of it, there's so many just little things that don't seem like it would be a big deal, but it can be.
Yeah, when we're like the whole crew that was working on the telescope, you can't have anything in your pockets. You can't have rings on your hands. You can't have anything loose on you when you're working on the telescope.
Yeah, right.
So, and if you have a tool in your hand, it has to have a tether attached to it.
Yeah.
So you can't physically drop the tool. And so there's all these safety precautions that we use.
Well, we're almost out of time. We have 2 more minutes, and let's take 2 more questions that we have here. One from Christopher. Are there supplies that are more difficult to get a hold of than other items?
Well, there was a few, but we planned so far ahead that we were able to get most of the stuff that we needed. Like I said, I started working about a year ago on this project, so I was ordering stuff a year ago just to make sure that we had everything that we
before
needed.
The supply chain issues became an issue.
Yeah, well, they were somewhat an issue back then, but just the chemicals to strip the mirror coating off took me about 3 or 4 months to get. The filaments took about a month or 2 to get, things like that.
Okay.
And so from previous coatings, we had a pretty good idea of all the supplies and things that we needed. So we were a step ahead when we started this around.
We have time for one more question, and what a great person to end with. Kay Corbin, a fabulous supporter and friend of Lowell Observatory for so long. She asked, does his mirror need to be electrostatically charged to receive the aluminum coating?
No, we don't. It's not charged at all. Yeah, it's just sitting in there. So we do cool the coating chamber quite a bit. So Yeah.
Okay, like we could talk about this all night. This is what always happens. It goes really fast. The process, you say the mirror has to be recoded, but when you realize the magnitude, the scale of things,
Oh, yeah.
in astronomy, we talk about really big and really small.
Mm-hmm.
And we think about the thinness of that mirror coating, for instance, to see, allows us to see vast distances. It's really remarkable to see the process. And you and your team, again, done such a great job with it.
Mm-hmm.
So thank you for joining us, and thanks for giving us a reason to talk about this.
Sure.
And thank everybody for joining us tonight. Nate and Maddie, our behind the scenes team, making everything work well. Thanks to everybody, and we'll see you next time as we continue celebrating the Lowell Discovery Telescope and its 10th anniversary. Thanks, and have a great night.